Hello there and welcome back. I hope you're having a wonderful day today. For today's discussion, we'll be continuing on with the equilibrium reactions, discussing how reaction conditions affect equilibrium. We'll be talking about Le Chatelier's principle and focusing on different factors that can shift the reaction. Le Chatelier's principle states that when a chemical equilibrium is upset or changed, then the equilibrium will shift in order to adjust for this change. Such factors that can change these conditions of a reaction include concentration, change in pressure, typically caused by a change in volume, or a change in temperature. As we go over this topic, we will be filling in the following table, including disturbance, observed change in equilibrium, how the reaction shifts, and the effect on K. Make sure as we go through each part, you are also writing them down for future reference. We have already discussed how a reaction shifts left to right in respect to the reaction quotient for concentration. But as a quick overview, let's look at the following equilibrium reaction of phosphorus trichloride and chlorine gas, which forms phosphorus pentachloride. It is important when you do equilibrium questions that you always write out what Q is equal to. In this case, it is PCl5 divided by PCl3 and Cl2. Let's look at what happens if we were to add more reactants, such as chlorine gas, to the system. If we look at the reaction quotient as we increase chlorine gas, then the value of Q decreases. So Q is less than K. We have now upset the chemical equilibrium, so in order for the reaction to reach equilibrium, the reaction shifts to the right. This means that the added reactant is consumed and more product is produced. Kc is not affected when concentrations are added or removed. If we were to remove a reactant in this scenario, such as chlorine gas, we yet again disturb the reaction, and as chlorine gas decreases, Qc becomes larger than Kc. In order to account for this, the change in equilibrium shifts left and produces more reactants to account for the change. Similarly, if you add product, then Qc becomes greater than Kc, which causes the reaction to shift to the left, producing more reactants. If you remove product, then the reaction shifts to the right to produce more products. Changes in pressure or volume also have a large effect on equilibrium systems. However, a change in pressure only has a measurable effect in the systems in which gases are involved, and the total number of gas molecules change in a chemical reaction. An easy way to determine when the total number of moles changes is to look at the balance equation and compare the moles of gas on the reactants and product side. For example, if we continue with the previous reaction, on the left side we have 2 moles for the reactants and 1 mole for the product side. A few things to keep in mind is that pressure and volume are inversely proportional to each other. Recall from Boyle's law. If the volume decreases, the pressure increases, so in order for the reaction to reduce, it shifts to the side that has the smallest number of gas molecules. If the volume increases, the pressure decreases, and as a result, the reaction shifts to the side that has the larger amount of gas molecules. For example, for the previous reaction, if we decrease the volume, the pressure increases, so the reaction shifts to the side with a lower number of gas molecules, and in this case, favors the production of PCl5, because it has fewer gas molecules. What happens when the total amount of gas molecules does not change? Well, because the change in volume has the same effect for both sides of the equation, there is no effect on the equilibrium in this case. In respect to the factors that we have covered, concentration and pressure does not alter the value of K. However, a change in temperature affects Kc. In order to understand why, let's focus on the enthalpy of a reaction with the same example. For the forward reaction, it is exothermic, which, if we recall, means the reaction produces heat. Because the enthalpy is less than 0, the reverse reaction is endothermic, because the enthalpy for the reaction is greater than 0. Now let's consider temperature as a component in this system. If heat is added, then the temperature is increased, and if heat is removed, then temperature is decreased. As we have been discussing these disruptions, they will shift the reaction to the left or to the right. Therefore, as temperature is increased, so heat is added, and then the reaction will shift to favor the endothermic direction. The reason for this is to relieve the stress of the additional heat. Whereas if we decrease temperature, heat is removed, it then favors the exothermic direction. The Van 't Hoff equation relates the change in equilibrium constants in a chemical reaction to the change in temperature and is as followed. We can also rearrange this equation and solve for a given variable in the equation. A few things to note when using this equation is that temperature must be in Kelvin and R is a universal gas constant and is equal to 8.314 joule per mole Kelvin. The last topic that I want to emphasize for this lesson is to mention catalysts and the role in a reaction. We have previously talked about catalysts and how they speed up a reaction by lowering the activation energy. Catalysts shorten the time a reaction takes to reach equilibrium, but they do not change the equilibrium position. This simply means that if we had two reactions, one with a catalyst and without, once the system has reached equilibrium, both reactions will have the same concentration of products. The only difference, the reaction with the catalyst just reaches equilibrium faster. To review, in today's discussion, we looked at some of the factors that affect equilibrium. We saw how changes in temperature, concentration, and pressure can put stress on a system and cause the equilibrium to shift. We also learned how to predict changes in equilibrium using the Van 't Hoff equation. Until next time, thank you for joining me on Cafe con Chemistry, and have a wonderful day. Thank you.